Hello, I'm Devin Nash, and today I will be discussing section 14.6, directional derivatives and the gradient vector. And some things I will be going over is the directional derivatives, kind of the definition of that, and I'll be going over an example of a directional derivative, and then I will be explaining the gradient vector and the notation for that. And then I'd like to discuss a couple steps for problem solving and an example of a problem for that. And then I will be discussing maximizing the directional derivative and an example for that. So the first thing is the definition of a directional derivative. A directional derivative can be used to find the rate of change of a function of two or more variables in any given direction. And let's just say, for example, we have a map of the Nevada, California region with different areas of different temperature, and let's say we want to find the rate of change of temperature with respect to distance. So we could call the change in direction in the y f of y, and the change in temperature in the x direction f of x. But let's say we want to find the rate of change of temperature in, say, the southeast direction. Recall that the partial derivatives can be written as this form below. And let's say we have a similar map, still with different areas with respect to distance and changing temperature, and we want to travel along the line from Reno in the southeast direction. And let's say we're traveling in a unit vector I minus j. And in this case, we might not necessarily have to use this expression, because we can find the rate of change of temperature by taking the difference at intersect points where the temp changes, and then just divide by the distance between the 2 points, which is approximately 75 miles according to the key. So we'll just say the rate of change of temperature is 60 minus 50, 60 being the green area and 50 being the first area in the blue, and we'll take the difference divided by 75, and we get approximately 0.133 degrees Fahrenheit per mile. Now the next thing is theorem 3. If f is a differential function of x and y, then f has a directional derivative in the direction of any given unit vector u equals ab. The more commonly seen notation for a directional derivative can be written as du f xy equals fx times a plus fy times b. And I would just like to go over an example here. So the first example asks us to find the directional derivative, and the function is x cubed minus 3xy plus 2 plus 4y squared, and the unit vector is given by theta equals pi over 6, and we can convert this to polar and say that u equals ab, where a equals cosine theta and b equals sine theta, and we'll use this formula to calculate the directional derivative. And first we'll take f of x, which is 3x squared minus 3y, and multiply it by cosine of pi over 6, plus the partial derivative of y, which should be negative 3x plus 8y, and multiply by sine of pi over 6. And you simplify that to get 13 minus 3 root 3 over 2. The next thing I would like to discuss is the gradient vector. And the gradient vector can express a directional derivative as a dot product of two vectors, and can be written as du f xy equals gradient vector f xy times u. And in 2D, this can be written as partial derivative of x times I plus partial derivative of y times j. And in 3D, we can write this as the partial derivative of x times I plus the partial derivative of y times j plus the partial derivative of z times k, or the gradient vector f x, y, z times u. And when I do these problems, I like to solve them in a certain way. So when I set up these problems, the first step is I like to just find each partial derivative in terms of I, j, and k. And the next step, I like to plug in the points. So for example, they give us the vector 1, 2, 3, then I'll plug in those numbers 1, 2, and 3 for my partial derivative. And for the third step, I will take the unit vector v and take the magnitude of that and divide each vector by it. And then for the fourth step, I will take that v and I will multiply it by the gradient vector of, say, 1, 2, 3. And my final answer should be a scalar number. Another example for a gradient vector: evaluate the gradient vector fxy equals x over y, and they give us the point 4, 1, and u equals 3/5 and 4/5. So the first step, we'll take each partial derivative. The partial derivative of x is 1 over y, and the partial derivative of y is negative x over y squared. So the gradient vector f is positive 1 over y I minus x over y squared j. And for the second step, we'll plug in the points 4, 1 to get 1i minus 4j. And for the third step, we'll take the unit vector v, which is the square root of 3/5 squared plus 4/5 squared, and we get 1. So v is 3/5 I plus 4/5 j. And finally, we multiply the gradient vector 4, 1 times the unit vector v to get 1, negative 4 times 3/5 comma 4/5 using the dot product, and we get a scalar number of negative 13/5. And the next thing I would like to discuss is maximizing the directional derivative. So theorem 15 states that suppose f is a differentiable function of 2 or 3 variables. The maximum value of the directional derivative du fx is the form as shown, and it occurs when u has the same direction as the gradient vector. Maximizing the directional derivative can be useful to find the maximum rate of change or the electrical potential. And finally, I have an example for this. And let's say we're asked to find the maximum rate of change of f at the given point and the direction in which it occurs. F of xy equals 4y root x, and the point given is 4, 1. And the first step, again, we'll take each partial derivative. F of x is 2y over root x, and f of y is 4 root x. So the gradient vector f xy equals 2y over root xi plus 4 root xj. And for the second step, I will plug in my points, 4, 1, and we get I plus 8j. And so the max rate of change is the magnitude of 1i plus 8j, and we get root 65. And this will occur in the direction 1, 8.